And just over to the class, the main objective of the today class is for recording the material for you to prepare for the midterm exam. And the participation for today's class is voluntary. And yeah, today is national holiday and you should have holiday. But I think at least you need maybe 1 week to review this content in order to prepare for your midterm exam. So yeah, I decided to record the class from today and we'll share the Zoom record for you to review. In our midterm exam, the midterm will be on Tuesday, March 9 in the morning. And by the schedule, we have like 3 hours for the midterm exam, but actually maybe it depends on you, but maybe the fastest guy maybe can complete the exam problem within maybe 1 hour or less than that. And the midterm, as we mentioned in the course syllabus, that we have like 30 points for the midterm exam. We have 2 parts of the exam problem. The first part, you may need to derive a rotational matrix. So the content that you need to review is the fixed angle and the Euler angle. One of these will be in the midterm exam, but you need to review both types of the fixed angle and the Euler angle. You need to review how to derive the rotational matrix from rotating the X, the Y, and the Z axis about the fixed coordinate. Or maybe you need to rotate about the Z axis, Y, and X axis about the coordinate that attach to the rotating axis. And this take only 5 points. We give only 5 points for the part 1. In part two, actually just the knowledge we study from last week is enough for you to do the second part of the exam. If you could remember, last week we learned how to attach frame on robot links by the notation, the David-Hartenberg notation. And after we attach frame to robot arm, we learn how can we obtain the corresponding DH parameter of each joint. If robot has 3 links, for example, if the robot has the base link 0, has link 1, and has link 2, this will be link 0, have joint 1 and joint 2. This will be link 1 and link 2. If we have 2 links of the robot, we are not counting the link 0. If we have the 2 links of the robot, when we compose the table of the DH parameter, we will have link 1 and link 2. And for each link, we know that we have the link length, link twist, the offset, and the joint angle that correspond to each link. And we need to compose the table. We need to find the correct value of the joint parameter. So in the exam, the robot has 3 degrees of freedom, which means we have 3 joints. The joint can be the combination of the level joint and also prismatic joint. And we have 3 degrees of freedom. It means, yeah, we have 3 links, and you need to compose 12 parameters. And for the 3 links, the robot with the 3 links, or the robot with the 3 links, you need to attach frame. You need to have frame 0, frame 1, frame 2, and the end effector frame. It means that you need to attach 4 frames on the link of the robot. And this 4 frames, if you can correctly attach 4 frames, you can get 8 points. And of course, when you construct the table of the DH parameter, if you can fill all the correct parameter, you can get 6 points. And for the parameter, we have the homogeneous transform metric. We have the metric that relate to the rotation about the z-axis and the translational about the z-axis with the joint offset. And we have the translational about the x-axis with the link length and also the link twist. And by the information of this, we have the homogeneous transform that relate link I to the link I minus 1. And we have the rotational matrix and the B origin at respect to the A. And P I origin with respect to I minus 1. We have the homogeneous transform metric. Don't worry. In the exam, we will give this form of metric. You don't need to remember. Your task is to obtain the correct parameter and correctly put into the form of the metric, and you can compose the homogeneous transform metric that correspond to the link. We have 3 links, 3 movable links. So you need to compose the homogeneous transform of frame 1 with respect to the frame 0, frame 2 with respect to frame 1, and frame 3 with respect to frame 2. And to obtain the forward kinematic, you just find the product of the homogeneous transform. And the position will be this, and the orientation will be this component of the final relationship. So why do we need to come for today's class? Because from last week, we only learned about how to attach frame to the level joint. But today, we will introduce how can we attach frame to prismatic joint. Do you have any question about the exam? You can ask me now, or yeah, after you check the video and after you yourself study. If you have question, you can text it in some way, maybe in line or in some way. And our today's topics, we're still talking about the forward kinematics, but we will have few examples of how to attach frame to different type of the robot manipulator. We still need to review the rule for attaching frame on robot link. And again, we will show how can we obtain the DH parameter to construct a table of DH parameter. And we also show the metric for the homogeneous transform and the way to obtain the forward kinematic. Just a review, because we can complete, we have already completed this in last week. So today just a review from last week. But today we mainly focus on examples how to attach frame on different type of the industrial robot, especially for the robot that has prismatic joint. How can we attach frame to robot that has prismatic joint? And we already announced the information about our midterm exam. So yeah, to review, how can we attach frame to industrial robot? The first step we need to do is to write down the axis of all the joint. Write down the axis of all the joint, and the Z axis will be the axis of the joint, but the order of the Z axis will be one step back from the joint number. For example, your simple robot has one joint and has link 0 and has link 1. You need to draw the axis of the joint, and the axis of the joint will be Z axis. But the order of the Z axis, it will be frame 0, the Z axis of frame 0, which correspond to the joint 1. This is the thing we need to do first. The second step is to find the origin of frame 0. Origin of frame 0 can be anywhere on this axis, which make alter parameter, the DH parameter, to become 0 as many as possible. For example, we know that the x-axis should be the mutual perpendicular. The x-axis should be the mutual perpendicular. So you may set the x0 here, or you can set the x0 along the link. But of course, you may prefer to set the origin of the frame in the choice that it made alter parameter to become 0 as much as possible. And with many examples in our today class, you will get more clear idea on how can we select the origin of frame 0. And the base frame, and for the other frame, that is not the base frame. The origin of any frame will be on the mutual perpendicular between the Ci and Ci minus 1. We have the joint I and the axis is Ci minus 1, joint I plus 1, and the axis Ci. This is the mutual perpendicular line. The origin of the other frame should be on this line, the mutual perpendicular line that intersect with the Ci axis. So it should be here, is the origin of the other frames. The x-axis is the direction of the mutual perpendicular, and it points from the location that it intersects with Ci minus 1 and point to the axis Ci. It means the x-axis is on the mutual perpendicular line, but it needs to point from here to here, to this direction, because it needs to point from the Ci minus 1 axis to the Ci axis to be the positive direction of the x-axis. For the y-axis, nothing important, just follow the right-hand rule. And here are the relationship between the link parameter when we describe by the frame. Yeah, if we see this, we cannot remember, but let's see in the example. And in all the example, I will try to switch back for you to recheck the idea of this when we compose the table of the VH parameter. The explanation, the full explanation for this robot link, I have already taught it last week, but again, this robot has link 0 connect to the floor, and it has the joint 1 to rotate the cylinder about the vertical axis. And we have another revolute joint here, and it can lift up, and another revolute joint here can lift this angle up. So the first step, we need to tackle with this type of problem before we see the robot given by the problem. We need to redraw the robot in the picture that show the non-zero joint angle. Show the non-zero joint angle. In the first picture, all joint angle seems to be 0. In the second picture, we try to rotate it about the vertical axis so that we can see the change of the theta 1. For the link 2, it also lifts from the ground by the angle theta 2. For the link 3, we also lift it from the line of the link tool to see the angle difference. And to attach the frame to this robot, of course, the zero step is to redraw the robot to show joint angle non-zero joint angle. The zero step. The first step, we need to draw the line of the rotational axis of each joint, and we name the z-axis correspond to the joint axis of each joint, but the order, we need to begin from Z0 at joint 1, C1 at joint 2, C2 at joint 3. And here is the step 1. The step 2 is to find the base frame. The base frame, now we already have z-axis. For the base frame, we just need to know where should be the x-axis of the base frame. The x-axis can be on the floor, or can be on the top of the cylinder. We can select the x0 anywhere, but if we select the x0 on the same level, on the same height as the level of the C1, we can make the offset to become 0. So in this case, we decide to select x-axis on a level that have the offset from the floor, and it will be on the level at the joint axis of the C1. And the direction of x0 can go anywhere on the horizontal plane. It depends on in which direction you want to set it as the x of the global frame. In this case, the direction that point out from the plane will be the x0. And if the robot rotates clockwise with the theta 1, it will change the direction from x0 to the x1 direction. Here is how can we select the O0 and x0. The origin is at this point, and the x0 point in this direction. The author's origin for the author's frame. We also need to we need to know that the origin of the author frame will be on the mutual perpendicular between the z-axis. For example, O1 need to be on the mutual perpendicular between C0 and C1. So here, the C0 and the Z1 The mutual perpendicular between the C0 and the C1 is the radial direction. Here. So the X1, the O1 and X1 should be the mutual perpendicular between C0 and C1, and O1 should be on X1, and at the point that it intersects with C1. So O1 should be on the C1 axis, and O1 should be on the line that is the mutual perpendicular between C0 and C1. So let's see this picture. The mutual perpendicular that connects C0 and C1 is this line, but O1 should be on the C1 axis. So this is the O1 point, and the X1 direction is the direction of the mutual perpendicular. So the X1 is this axis. Using the same concept for the O2, the origin of frame 2, and the X of the frame 2, the origin of the frame 2 and the X-axis of the frame 2 for the X-axis of the frame 2, we need to draw the mutual perpendicular between the C1 and C2. The mutual perpendicular between C1 and C2 will be this and this. And the X2 is the mutual perpendicular between C1 and C2. And O2 should be on the C2. So here is the O2. And here is the X2 direction. We use the same way for the end effector here. In this case, we just want to put the origin of the final frame, on the end effector location. For the direction of the axis, we will have the explanation about the axis. In general, we may have two ways to select the direction for the end effector frame. The first way, we just set it in order that we can obtain as many as possible the zero value of the parameter, which means we will try to set the end effector frame in the same way we set the previous frame. Another possible way, we're gonna set the C-axis in the direction that normal to the gripper, and the X-axis will be the direction that the gripper moves. For example, if you have a gripper like this, you're gonna set the C-axis of the end effector point out from the gripper. And you know that for the gripper can extend the side of the gripper in this direction. So you're gonna put the X-axis of the end effector in the direction that the gripper moves. Here is another possible way. It depends on what you're gonna select for the final frame. to obtain the DH parameter, after we attach the frame, the link length AI, link length AI, link width, offset, and the joint angle. The link length AI is the direction between the axis Ci minus 1 and the axis Ci measure along the measure along the Xi minus 1. The link length is the distance between the Ci minus 1 and the Ci along Xi. Sorry. It means the link length AI is the distance between the Ci minus 1 and the Ci measure along the Xi. And link width is the angle between the Ci minus 1 and the Ci measure about the Xi by the right hand rule. It means that this is the direction of Ci minus 1. You need to use the right hand rule about the thumb should go in the X direction and the forefinger go to this direction, and then change the direction from Ci minus 1 to Ci, and then you can get the link width. So come back to here. The link length is measured from Ci minus 1 to Ci along Xi direction. We have C0 and we have C1. If we want to measure the distance between the C0 and C1 along the Xi direction, the distance is the radius of the cylinder. For the link width, it needs to measure about the Xi direction, which means your thumb should point along the Xi direction and forefinger will be in the Ci minus 1 and rotate to Ci. In this case, the thumb will point angle between Ci minus 1 to Ci about Xi axis. So the thumb point in the X1 direction. The finger point to the C0 and then rotate to C1. And this angle is 90 degrees. And it's linked with the offset is the direction from OI minus 1 to Xi along Ci. Along Ci minus 1. The offset is the direction measured from OI minus 1 to Xi and measure along Ci minus 1 from OI minus 1 to Xi along Ci minus 1. And here if we see the picture, the distance measure from O0, the distance measure from O0 to x1 and measure along Z0 axis. In this case, as I mentioned, that if we try to select the position of O0 in the same level as the joint axis C1, we can eliminate the link offset. We can make it to be 0. But if you set O0 somewhere, beneath the level of the joint axis here, you will find the joint offset. You will find the joint offset here. The last parameter is the joint axis. Joint axis is the angle difference between the x direction from xi minus 1 in this direction to xi in this direction. And joint angle is measured about the zi minus 1 axis, about this axis. So you need to find the angle difference between this line and this line about this axis. The parallel line of xi, is this one. And the angle between xi minus 1 and xi about this axis is equal to the joint angle theta 1. So come to here. The angle between xi minus 1 and xi about ci minus 1 will be the angle between x0 and x1. x1 measure about z0, which is the theta 1 angle. The angle between x0 and x1 measure about z0 will be theta 1. You can see the mark here, the star here. The meaning of the star is that, hey, in the 4 parameter of link 1, R is a constant, 90 degree is constant, D is also a constant, but theta 1 is a joint variable. If we can drive the theta 1 by a motor and we can change the value of the theta 1 by actuator, so we have the star on the theta 1. Okay, we still use the similar way to obtain the parameter of another joint for the link 2. The link length is the distance between ci minus 1 and ci along xi. So the link length is the distance between d1 to c2 along x2. So that length is L1. The twist is the angle difference between the z-axis. The axis has the same direction. So the link twist will be 0 degree. The joint angle is the angle between the xi minus 1 and xi about zi minus 1. So the angle will be the angle between xi and x2 about the C1. So the angle is theta 2 in this case. And again, if we put the same orientation of C2 to the C3, and yeah, X3 is along the length of the link. The parameter of the link 3 is in the same pattern of the link 2. After we get the parameter in the table, in the exam question, we will provide this metric. And in order to compose the homogeneous transform that relate link 1 to link 0, you need to put the variable of the link 1, this 4 parameter of the link 1, and you can compose the metric. How can we obtain this metric? We already explained about this in last week. To transform the frame from frame 0 to frame 1, to transform the frame 0 to frame 1, to transform from the frame I-1 to frame I, the process that we need to do is, of course, we need to rotate frame I-1 about the z-axis with the theta angle. Rotate about z-axis with the theta angle. And then we need to translate along the z-axis with the distance di. So we need to translate along the z-axis with the distance di. And then we need to transform, we need to translate from this point to this point, which means we need to translate along the x-axis with the distance ai. So this is the third step, translate along the x-axis with the distance ai. And the final step, we need to rotate about the x-axis. We need to rotate about the x-axis to change the direction by alpha angle, so that we transform this frame to this frame. We need 4 steps. The last step is to rotate about the x-axis with alpha angle. So the rotational matrix about the CI, we need to obtain the rotational matrix of the CI and have 9 components. And for the pure rotation, the origin of the frame doesn't change. This is not 0, but this will be 9 parameter of the rotational matrix that correspond to the rotation about the z-axis with the theta I. You may think about this. We have x, y, and z. And when you rotate about the z-axis, you're gonna have the z palm, the x palm, and the y palm. And when you rotate with this angle, the rotational matrix here is x palm dot x, x palm dot original y, x palm dot original z, in the first column, and then the y plum dot x, y plum dot y original, y plum dot z original, and yeah, you need to obtain the dot product of this, and then you can compose the rotational matrix. But of course, the origin of the frame doesn't change by the pure rotational. So the component here are 0. And you have the 4x4 matrix that correspond to this. For the pure translational in Z direction, the rotational matrix, it doesn't change the orientation. So this is the rotational matrix. And for the pure translation in the Z axis, you have only di. So now this is this and this. You may need to construct 4x4 matrix of this and 4x4 matrix of this. And if you have the product of the 4 matrix, finally you can derive this one. Yeah, for the derivation, please check our last week video. But in the exam, we will give you this matrix. You just know how to put the value of this to compose the matrix. P1 refer to 0, 3, 2 with respect to the 1, and 3 that respect to 2. And if you want to obtain the forward kinematic, you should be able to relate the final link or the origin of the final frame, the origin here, with respect to the frame 0. So the idea is, yes, you need to multiply, you need to find the product of the metric from the first metric to the final metric. And then if we want to know the position, XYZ position of the origin of the final frame, this is the position of frame N origin with respect to frame 0. And this is the orientation of frame N with respect to the original XYZ of the frame 0. So I hope you do something with this exercise. This exercise is not complicated, and you should do it as a homework, like voluntary homework to recheck how can you attach frame to this planar robot arm. But today we will have a few more examples. Okay, if we can complete the example, we will come back to here, okay? This is the 3 level joint robot. This is the 3 level joint robot. We need to attach frame and obtain the table of the H parameter. As I mentioned, the 0 step we need to do, is to redraw the picture. And show the non-zero joint angle. What's gonna happen if we rotate this first joint about the vertical axis? If we not rotate, this line may go in this direction. But after we rotate the joint, about the vertical axis, if we rotate the joint by theta 1 about the vertical axis, what we have is we change this direction by theta 1. And what happened if we also rotate this with theta 2, of course, it will lift in the vertical direction with theta 2. The theta 1 is the rotation in the horizontal. The rotation of theta 1 is rotation about the vertical axis. So the change in this direction is on the horizontal plane. But the change for the theta 2, we are elevating the link in the vertical direction. Be careful to see the meaning of the image. And of course, when we elevating, we're gonna have the joint here, and the joint will be at this point. If we elevating this joint with the theta 3, it means we have the theta 3 here. We elevating this joint with theta 3. And this is the end effector. And in order to attach frame, what is the first step when we need to do to attach frame? We know the joint axis, so you don't need to think much. For the first step, you just draw C0, C1, C2 along the direction of the joint axis of the level root joint. This is the first step. In our problem, we need to compose the table of the H parameter. How many links do we have? We have 3 joints. So the movable link, we have 3 joints. So the movable link, we have link 1, link 2, link 3. We are not going to write the link 0. If we have 3 joints, we have 3 movable links, link 1, 2, 3. The DH parameter will be the link length AI, the link width alpha I, the link offset DI, and the joint angle theta I. The link length is the direction, the distance between CI minus 1 to CI along XI axis. The link length is the distance between CI minus 1 to CI along XI axis. Link width also the angle between CI minus 1 to the direction of CI and measure about XI axis. The joint offset is the distance between OI minus 1, the origin of the frame I minus 1, to the x-axis of the frame I. And the link offset is measured along the axis I minus 1 along this, measure from the origin to the x along the z-axis I minus 1. The angle is the angle between the x-axis of I minus 1 and the direction of xi. And we also measure about c I minus 1. For the distance along, for the angle about, for the distance along. The zero step to attach the frame is to redraw the picture and show the non-zero joint angle orientation. And the first step is to draw the z-axis that correspond to the joint. The joint 1 is the direction of C0. The joint 2, direction C1. The joint 3, the C2. And the end effector, you can decide the direction of the Z will be parallel to this or will point normal, point in the same line with the link, or point normal to the gripper. It depends on you. But in this case, to make it easy, yeah, I decide to put the z-axis of the end effector point to this direction. The second step is to locate the base frame. To locate the base frame. Okay, now the z-axis is in the vertical direction. I can write down the base frame. For example, if I set x0 here on the floor, if I set x0 here on the floor, the origin of the base frame will be on the floor. With this idea, if you want to find the offset, the offset is the distance measured from O0 to xi. C1 is this line. So the xi should be on this level, on the plane with the height, on the plane with the height. The distance, the length here will L1, L2, and L3. The length of the arm will be L1, L2, and L3. If we set the origin of frame 0 on the floor, if we want to find the link offset, we need to find the distance from origin 0 to x1 along C0, which means, yeah, the offset should be something like here. But we have another choice. Why not we put the origin of frame 0 at this point? Why not we put the origin of the frame 0 at this point, so that it will be on the same level as the x1, and we can eliminate the value of the offset. We also can do that. But yeah, if you don't know, and if you decide to put the O0 or the origin of frame 0 on the floor, you can do that, and we can continue. It not conflict with the rule. You can put origin of the bed frame anywhere on the C0, but it should be better to put somewhere that author parameter becomes 0. But if you don't know, you just put origin on the floor like this. So now we already have x0 and z0. So it means we already attached the first frame, the 0 frame, to the robot. How about the first frame? We have z1, and where should be x1 direction? Where should be x1 direction? x1 direction. The C1 is the direction of the joint. The C1 is the direction of the joint, and x1 is the mutual perpendicular. X1 should be the mutual perpendicular between C0 and C1 and pass through the origin of the frame 1. Let's see the mutual perpendicular between the C0 and C1. Now we can see that C0 and C1 intersect. C0 and C1 intersect. The mutual perpendicular has two solutions. If this line and this line are intersect, the mutual perpendicular can be one that point out from the paper and another one that point in the paper. We have two possible solutions. In this case, C0 and C1 intersect. X1 can be the direction that point to this direction or point to another direction. We can select X1 in two possible ways. If we select X1 in this way, if we select X1 in this way, if we want to find the joint angle, the joint angle of the link 1 is the direction between the X0 and X1 measure about Z0 it will be this angle. But if we select x1 in the opposite direction, we need to plus it by 180 degrees, which increase the complication. So we select the x1 to this direction. Okay, come back to here. The link length is the distance between the C0 and C1 along x1. But in this case, the C0 and C1 intersect. So the link length will be 0. The link twist is the angle between C0 and C1 and measure about x1. So we need to use the right hand rule. The thumb point along x1. The thumb point along x1. And forefinger point to the C0. And then grab your hand so that the finger move to C1. You can see that C0 and C1 has 90 degree difference about the x-axis, the x1 axis. How about the offset? The offset is the distance measured from the origin of the zero frame to the x1 axis and measure along C0 axis. So that offset with this picture, that offset is L1. The angle, the joint angle of the first link, the joint angle is the angle between x0 and x1, measure about C0. X0 is this direction, x0 is this direction. X1 is this direction. About the C0, about this. So that angle is theta1, and theta1 is joint angle. We can change the value by actuator. Now we already attached the frame 0 and frame 1. And we already obtained the parameter of link 1. How about link 2? How about link 2? We have C2 already in the axis of the joint. The x2 should be the mutual perpendicular between x2 should be the mutual perpendicular between C1 and C2, right? So when we see here, x2 should be the mutual perpendicular between C1 and C2. So x2 should be in this direction. X2 should be in this direction. X3 should be the mutual perpendicular between C2 and C3. So X3 should be in this direction. So how can we derive the parameter? The length of the link 2. The length of the link 2 is measured from C1 to C2 along X2. C1 to C2 along X2. So of course, the distance will be this length, L2. So the length between C1 and C2 along X2 axis will be the length L2. The twist is the angle difference between C1 and C2. It has the same direction, so the angle difference is 0. The offset of the link tool is the distance measured from O1 to X2 along C1. The distance from O1 is this point to X2. O1 is on X2. So the distance, the offset is 0. And the angle of link 2 is the angle between X1 and X2 measured about C1. The angle between X1 and X2 measure about C1 is theta 2. And this is joint angle, joint variable, because it can control by actuator. With the same concept, the length of the link tree is the distance between C2 and C3 along X3. So is this length L3. The twist is the angle difference between C2 and C3. It has the same direction, so angle will be 0. The offset is the distance from O2 to X3 along C2, but O2 is already on X3, so offset will be 0. And the angle is the angle of X3 compared to X2 about the C2 axis. So the angle will be theta 3, which is the joint variable. So this is the 3-level loop joint robot. How about the robot with 3 prismatic robot? This is new for us, but the idea still be similar to for the level loop robot. The first thing you need to do with the prismatic, you also need to line the direction Z in the direction of the joint offset. The level loop joint, the variable is the joint angle, is rotate the joint angle. For prismatic, the joint variable is the link offset. Prismatic change the link offset along the Z axis. Prismatic change the offset, change the joint offset along the Z axis. So to attach frame for the prismatic robot, what we need to do is just put the z-axis along the direction of the offset, direction of the motion. This prismatic robot, what they can do is they can translate in the direction of the joint. If joint 1 change the variable d1, it will push the things to that direction, or come back to this direction. If joint 2 change the variable d, it can move the things to the left and the right hand side. If joint 3 change the prismatic, change the d, it will lift the thing up and down. So the first step for prismatic is to direct the z direction to the robot. The second step, of course, we need to find the base frame, but let's draw the table. The link I, the parameter length, link to width, link offset, and angle. The length L, I, the twist alpha I, the offset di, the angle theta I. And in this case, we have 3 joints. We have 3 prismatic joints. Of course, we have 3 movable links. We have 3 movable links. We already attached the z-axis, right? And by the definition of the twist, if you could remember, the twist is the angle between ci minus 1 to ci about xi to ci about xi. In this case, what should be the link length? In this case, what should be the link length? The link length is the distance between ci along xi. But in this case, z1 and z0 intersect. So the length will be 0. The twist is the angle measured from c0 to c1 about x1. Measure from z0 to c1 about x1. What should be the direction of the x1? We can draw x1 downward or x1 upward. By the right-hand rule, if you want to get the positive 90 degree, you may prefer x1 to point downward instead of point upward, so that by the right-hand rule, you can get positive 90 degree. In this case, if you point x1 upward, the twist will be minus 90 degree. And offset is the distance from O0 to x1 along C I minus 1. Offset is the distance from O0 to x1 along Z0. O0 to x1 along Z0. So the offset here is depend on the D1. The offset here, I hope you still can see the screen. No black screen, right?
Oh ครับ
ครับขอบคุณครับ the offset will be the distance from O0 to x1 along Z0 from O0 to x1 along Z0. So it depends on the variable of the linear actuator. If the linear actuator move far there, the distance d1 will increase. If the linear actuator or the prismatic joint move to move the x1 close to the O0, this value will smaller. The joint angle is the angle between xi minus 1 and xi about ci minus 1. So now you already set the x1 direction. The joint angle is the angle between x0 and x1. The good way, if we want the parameter to be 0, you can set the x0 in the same direction with the x1 so that you can make this to be 0. But if you select x0 in other direction, this value will not be 0. How about link 2? The link length of the link 2 is the distance between C1 and C2. The C1. I'm sorry. This is 2, not 3. And yeah, this is 2, not 3. The joint 1 frame 0, the joint 2 frame 1, and the joint 3 frame 2. Okay. The distance between C1 and C2, of course the C1 and C2 intersect, so the distance will be 0. The twist is the angle between C1 and C2. If you want the twist to be 90 degrees positive, the direction of x2 should be in that direction. If you use x2 in this direction, the twist will be minus 90 degrees. So if you select x2 in that direction, the twist will be positive 90 degrees because the twist need to use the right hand rule about the x2 direction from C1 to C2 about x2, so you get 90 degrees. the offset is the distance between O1 and X2. O1 is this position, X2 is here, and measure about C1. C1 is this direction. So the distance between O1 and X2 is the joint variable D2. D2. D1 is this distance and D2 is this distance. And the angle, the joint angle, is the angle difference between X1 and X2. X1 and X2 measure about C1. X1, X2 measure about C1. So your thumb need to be on the direction of C1. Your finger point in the X1 direction. And then switch 90 degrees to the direction of X2. So the triangle is 90 degrees here, but the triangle here is fixed, is constant, because this robot is prismatic robot. The joint variable, the star, is joint variable and can change. This prismatic robot, the joint variable is the offset, and the angle, the joint angle, is constant. How about the link tree? The link tree, the link length is the distance between C2 and C3. Again, the I'm sorry, C1 and C2. The link length is the distance between C1 and C2, and it intersects. So the length is 0. The twist is measured from C1 to C2 about X2. About X2. Oh, we already do this. Okay, I have one mistake. I forgot to put the end effector frame. The end effector frame. The end effector frame here, I will point it in the same direction with the frame 2, so that we can reduce the complication. The X3, the C3 and C2 have the same direction. The X3 and X2 have the same direction, but origin of the frame 3 is at the end point. Origin of the frame 3 is at the end point. Again, I'm sorry. The length is the distance between C2 and C3. C2 and C3. And C2 and C3 are on the same line. The length will be 0. The twist is the angle between C2 and CT. Angle also the same. So this also 0. The offset will be the distance from O2 to X3 along C2. O2 to X3 along C2. So the distance here is controlled by the offset. Controlled by the offset. And the angle is the angle between X and X, X3 and X2. And they point in the same direction. So the joint angle will be 0 in this case. So for the 3 prismatic robot, we have 3 joint variable. And we have 2 more. Example, should I break or you can continue?
We can keep going.
Okay, good.
But before that, I have a question on example 1 ครับ.
Okay.
I think it's gonna be how you put the origin, the O0, and how it affects the
variable.
The offset, right? You said if you set the origin to the ground, to the ground link, the offset will be L1, correct?
Yes.
But on the other hand, if we set the O0, O1 at the same, at the which, how should I refer?
It should be O0, not O1, right?
So if you set O0 the same point as O1, the length is 0, right? But the offset is also 0, correct?
Yes. Here also will be 0. Yeah, but it will be easy in the calculation, but when you interpret, when you want to explain, when you want to relate your mathematical expression with your physical system, you should keep in mind that, hey, the global frame, the base frame of the robot in the physical system, it is not on the floor, but it is somewhere above from the floor with the length L1. Just only this, yeah.
So in this case, which is the better O0 point, the ground?
For me, I may put it here. I mean, put it on the point that make the parameter will be 0. Yeah, because when we put everything into the metric, I mean, every time if we have L1, you need to multiply it by L1. But if it's 0, maybe it can reduce the computation time. But finally, in the physical system, we just keep in mind that the origin is far from the ground. This problem is similar to maybe many times I draw the picture of this planar level robot. Many times I draw the picture of this planar level robot. Now it seems like you have 2 possible ways to set the reference frame. You may, if we are not talking about the industrial robot, if we are talking about the normal kinematic consideration, of course, by the global meaning, the X and Y coordinate, X should be on the floor and Y should be in the vertical direction. But many times you may set X here and Y here in order that you can derive X equal to L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2 and Y equal to L1 sine theta 1 plus L2 sine theta 1 plus theta 2. Instead of having this offset, yes, this is the explanation for this. Yeah.
Okay, so it looks more a little bit more beautiful, but we have no way of knowing anything about whether the robot is offset off the ground.
Yes.
Right.
Yes.
If we change
Yes.
the origin point like that.
Yes. Yes. I mean, when you are controlling the robot, you should keep in mind that, hey, our current origin is offset from the ground. Yeah. And if you put the origin of the frame on the ground and you want to grab something here, the object that you need to grab will be x with 0 in coordinate. But if you use this coordinate, when you want to grab something on the ground, you need to remind that this position should be x coordinate and minus L0. Did you get the meaning?
Yeah.
Yes, yes. Yeah. But yeah, it is like this. If you have table, and you put something on table, you also have the table height. And at that time, it also depends on which coordinate you are going to use and what should be the height of the table in that coordinate. And finally, it seems like it's not that much important that where you're gonna select this. I mean, if you have the table, you cannot see the advantage of this anymore. But by this, you still can see the advantage because in the calculation, you don't need to plus L0 for the y position. Yeah.
Okay, I see.
Yes, yes. Okay. This seems to be easy. We have only one level load and one prismatic. So yeah, our idea, we just draw the axis. This is joint 1, right? Joint 1. So the axis should be Z0. And this one, the direction of the prismatic will be the direction of Z1. And the joint axis of the prismatic is along the line. So we still don't know where is the origin of the frame 1. So the DH parameter table, we have only link 1 and link 2. And the parameter will be length, twist, offset, and the angle. The length, the twist, the offset, and the angle. For the link 1, now we know only the direction of the z-axis. Hey, if we want to obtain the link length, what should be the link length? The link length is the mutual perpendicular the z0 axis is somewhere. The mutual perpendicular will be the line that perpendicular to the C1 and also perpendicular to the C0. The mutual perpendicular will be this line. So it means, yeah, we need to know this dimension of the robot. We need to know this dimension of the robot. And the link length will be this dimension. The mutual perpendicular between the C0 and C1 will be the link length 1. How about the link to width? If we want to find the link to width, you need to use the right-hand rule to find the direction difference between Ci minus 1 to Ci about x I minus 1. I'm not sure that the length, no, about xi, I'm sorry. The link to width, you need to find the angle difference between C0 and C1 about the xi direction. So can you imagine what should be the x1 direction, the x0 and x1 direction? We need to find the angle difference between the theta 0 and theta 1 about x1 direction. What should be the direction of x1 in this case? So x1 should be this. Why? At least we know that the x1 should be the mutual perpendicular and should be the direction of the link length. The x1 should be the mutual perpendicular between C0 and C1. And the link length L is the length that measures along the mutual perpendicular along the x1. And the link to width is the angle difference between C0 and C1. Now imagine that you have your thumb point on the x1 and your forefinger need to point along the C0. And then you use the right-hand rule to find the angle between C0 and C1. And in this case, you can see that the twist will be 90 degrees. The offset is the distance from OI minus 1 to XI along CI minus 1. O0 is this point. You need to measure the distance from O0 to X1 along C0. In this case, we can see that the O0 is already on X1. So the offset will be 0. The offset will be 0. How about the angle? The angle will be the angle difference between xi minus 1 to xi about ci minus 1. So it should be direction difference between x0 and x1 about c0. Now x1 is point to that direction, but you still didn't set the x0. You just know that z0 is point out from the paper, the screen. Of course, you may set x0 to that direction. It's also possible. Or by usual, you always set x in the horizontal plane. So you may set x0 in this direction. But if you set x0 to this direction, if you set x0 to this direction, please keep in mind that the joint angle that drive by actuator will affect the joint angle. But in this case, the real joint angle is the angle difference between x0 and x1 about c0. The joint angle should measure from x0 to x1. So here, the angle will be 90 degrees plus theta 1. And theta 1 will be the joint variable that drives by actuator. So now it depends. If you select x0 here, the joint angle which measure from the x0 to x1 will be 90 degrees plus theta 1, which is the joint variable. Or if you set the x0 here, the joint angle will be just only theta 1. It depends on you in which direction you're gonna set the x0 for this case. And for the link tool, now we only have the z1, which is the z-axis of the second frame. We still need to set the x direction of the x1 already set here, right? Okay, so now we already set the frame. We just only need to find the parameter. What is the length? What is the length of link 2? The length of link 2 is the distance between C1 and C2. Oh, again, I make a mistake again. I always forget to put the frame to the end effector. In this case, we need to find the position of the end effector, and we need to attach frame to that position also. In order to make it easy, I set the orientation of the frame 2 in the same direction with frame 1, which means C2, same direction with C1, and X1, X2, same direction with X1, and just have an offset here between them. And okay, the length is the direction between C1 and C2. C1 and C2 in the same line, length is 0. The twist, also the angle difference between the C1 and C2. So twist is also 0 degree. Offset is the distance from O1 to X2 along C1. The distance from O1 2x2 along C1 will be this distance, and this distance is driven by the actuator. And there is one point here I want to let you know, and it's important. Hey, maybe in the real application, what you can measure will be this distance, because when you use linear actuator, the linear actuator can control the position of its arm from the point to the end point. But this distance is the robot geometry, and maybe the sensor on the robot and the actuator don't know this distance, but you are the robot designer. You know this parameter D, and you know that what the robot can read is D star. The offset, by the idea, the offset is the distance between O1 to X2 when we measure along C1. O1 to X2 and measure along C1. So the offset will be D plus the joy variable. We have one constant parameter and the joy variable. It depends in the robot if you can directly measure this distance. You may not need to consider about the D, because just D will be the offset. But it depends on how you define the constant in your robot. If you want to define the D, you will have D plus the joy variable. If you ignore D and you measure the D star for the whole length of the offset, you just use the D star. And for the angle is the difference between the X direction. Of course, X1 and X2 has the same direction. So the joint angle will be 0. And this is the last example for today. In this robot, we have the base frame. And the joint 1 is the level loop joint that rotates about the vertical axis. It's this one. It's the level loop joint. The stator or the level loop joint like connect to the ground and it rotates the level loop joint. And on the level loop joint, we have one prismatic. The prismatic means you can slide to the right and to the left hand side with this prismatic. Joint 2 is prismatic. Joint 1 is level loop. The last joint before the end effector is another level loop that can provide the rotation of this. So for this problem, the 0 step, we may try to draw the robot when we have the joint angle. It means that here we have the cylinder that put on the floor. And yes, we may set the x0. We may set the x0 on the floor. And on this point, if the robot doesn't rotate, it will lie into this direction. But if it rotates, it will go to that direction and have the prismatic joint. And the prismatic joint connect to another revolute joint and connect to the arm. Okay, at least now, what we need to do is we need to point the Z direction. The Z0 is along the joint 1. The Z1 is along the prismatic. The C1 is along the prismatic. So yes, C1 is this direction. The C2 is also along the axis of rotation of the revolute joint. The last thing that I forgot to put the final frame, right? So in this case, I try to point the last frame at the end effector point to the same direction with C2. So in this case, we have 3 joints. And we have link 1, link 2, and link 3. We have link 0, link 1, 2, 3. And we should have from frame 0 to frame 3. And yes, let's see frame by frame. We have the C0 in the axis of rotation of the joint 1. We have C1 in the axis of the prismatic joint. And we have C2 in the axis of the revolute joint. And we have C3 in the same direction with C2, but the origin of the frame 3 is at the endpoint position. So the parameter link length alpha, offset, and angle. The link length is the distance between Ci minus 1 and Ci along Xi. Link length is the distance between Ci minus 1 to Ci along Xi. Tau width is the angle. And the offset is OI minus 1 to Xi along Ci minus 1. Offset OI minus 1 to Xi along Ci minus 1. And the angle is Xi minus 1 to Xi about Ci minus 1. So for the first link, we need to find the distance between Z0 and Z1 along X1. The C0 is point upward. C1 is the prismatic axis and it intersects. So the length will be 0. The twist is the angle between C0 and C1 about xi. So xi should be x1. Where we gonna point x1? X1 perpendicular. X1 perpendicular to the C1. And on the horizontal plane, C1 always on the horizontal plane, right? Just rotate. X1 also on the horizontal plane and perpendicular to C1. If we find the direction difference between C0 and C1 about X1, it will be 90 degrees. The offset is O0 to X1 along C0. O0 to X1 along C0. So we need to define this length. This length may be the height. Maybe the height. So the height, the offset is the distance between O0 and X1 along Z0. The offset will be the height in this case. How about the angle? Angle will be the angle difference between X0 and X1 about C0. You can see that here, if this rotates by theta 1, if this rotates about the C0 axis on the horizontal plane with the angle theta 1, the angle difference between X0 and X1, if you see from the top view, X0 will be in this direction. If you see from the top view, X0 will be in this direction. And when it rotates by the angle theta, the Z1 and the X1 will change the direction if you see from the top view. So it means that the angle difference between X0 and X1 will be 90 degrees plus the theta 1 plus the theta 1. And theta 1 is the joint variable. H is constant, 90 degrees is constant, but theta 1 is variable. The link length is the distance between Z1 and Z2. Z1 and Z2 are in the same line, so the length will be 0. The twist, the angle difference between C1 and C2, also 0 because it has the same direction. The offset is the distance from O1 to x2 along C1. D2 is the distance from O1 to x2 along C1. O1 is this point. X2, we still didn't put the x2, right? But x2 now I decide to put x2 on the top of the level joint. I put O2 here and x2 on the top of the level joint here, and I put x2 in the parallel direction with x1 in this case. So the offset is the distance between O1 to the x2 along the C1 direction, which means this distance and this distance is controlled by the prismatic and is a joint variable that controlled by the prismatic with the joint variable d. How about the joint angle? The angle is the angle between x1 and x2 about C2. x1 and x2 about C2. If x1 and x2 has the same direction, x1 and x2 has the same direction, the angle will be 0. For the link, at the end effector, we have the effect of the level load. The z-axis of the end effector point in the same direction with C2, but the x-axis of the end effector, x3, is the effect of the rotation here. Is the effect of the rotation here. If you rotate by theta degree, theta 2, you can create the direction difference between theta 2, between x2 and x3. If you see this picture, it seems like, hey, you have x2 in that direction, and this is x3. This is x2, and the angle difference between x2 and x3 is controlled by the theta 3. So if you find the link length between C2 and C3, the length will be 0 because the C2 and C3 are on the same axis. If you find the link twist, the twist also 0 because C2 and C3 has the same direction. If you find the offset of the C2 and C3 will be the offset between here. The offset between the top of the level joint and the end effector. Of course, we have one offset. Yeah, it can be D2, which is the constant offset. And for the angle between x2 and xt measure about C2. Angle between x2 and x3 measure about C2 will be the joint angle that is controlled by the third revolute joint. So here is the parameter of this robot. And yeah, if we go back to this example, what you need to do is you need to have the z-axis of C0, of C1, and of the C2. The n effector, yeah, you may try to have the z direction that's normal to the n effector and may have the x direction in the direction that the gripper move. You may attach the frame like this, and yes, you may set the x-axis on the horizontal plane, and y-axis will be follow the right-hand rule, and the mutual perpendicular between C0 and C1 will be the direction of x1. The mutual perpendicular between C1 and C2 will be the direction of the x2. Now you already set all the frame for this robot, and you will try to obtain the table of link. How many link we have? We have link 1, link 2, and link 3. Because we have 1, 2, and 3 revolute joint. So you have link 1, link 2, and link 3. And the parameter will be length, width, offset, and angle. And you will try to derive the parameter from here. And when you get the parameter, you got the homogeneous transform by this matrix. And to obtain the forward kinematic, you find the product of the matrix. I hadn't put much effort to teach you how to do the product of the metric, but I expect that you know how to do it, right? So please practice by yourself. For example, from this example, you compose the parameter, try to construct the metric, and obtain the product of the metric, and see what is the position of the endpoint with respect to the global frame. And this should be enough for the midterm exam. And don't forget to review about the fixed angle and Euler angle. So yeah, that's all for today. Do you have any question?
Do we have to are we allow any calculators that can compute a more than 3x3 matrices in the midterm exam?
You know that in our exam, I'm not sure I understand your question, but I will answer in two ways. The first way is actually we don't need to bring the calculator inside, because all the variable or the parameter will be given in the terms of variable, no numerical value, and you need to compute it in the terms of the variable. And the maximum degree of freedom, yeah, of course, it's 3 degrees of freedom. So at least you need to be able to do the product of 3 metric, yeah. So the idea is you do the product of the two metric first, and you have the product, and then you continue with the second pair. Yeah.
โอเค
ครับ That's all. I only have the live chat of Gong and maybe Jump. So after I have the Zoom link for the record, I will send to Gong. Okay.
โอเคครับ
Maybe by today's evening. Yeah. โอเคครับ วันนี้มีแค่นี้ มีคำถามอื่นอยากถามเป็นภาษาไทยเปล่าหรือได้แล้ว
คือเด่นอะเป็นภาษาไทย